This is an introduction to Chapter 2 in the book Problem Solving with Differential and Integral Calculus. The one concept that differentiates calculus from algebra is the concept of the infinitesimal. In this chapter, we're going to explore the infinitesimal difference. Chapter 1 was just algebra. Here we're going to say, what the heck is dx? This infinitesimal that's very hard to wrap your heads around. If you're going to use calculus to solve problems, you need to understand the idea of the differential. I've talked to many calculus teachers and they say the students just can't understand what dx is. We just have to give them some derivatives, some rules for taking derivatives, the product rule, the quotient rule, etc., some rules for doing integrals. This is integration by parts, etc., without understanding what dx is. But if you're going to use calculus as a tool to solve problems, you have to understand the differential. And we're going to spend the entire chapter trying to understand what the heck is dx. The human mind is not built to understand infinitesimals, just like it's not built to understand the concept of infinity. So here's an example of not understanding infinity. There's a hotel, infinite number of rooms. Guy walks in, he says, "I'd like a room." He says, "I'm sorry, we're full." And he says, "All right, I'll go somewhere else." And then on the way out, he says, "Wait a minute. How about if everybody just moves up one room? And I'll take room 1. And the proprietor says, "Ah, that's a good idea." And they tried it, and it worked. So infinity plus 1, what's that? Is it still infinity? The rooms were full, and they put another room in there. The infinitesimal is like 1 over infinity. The infinite is infinitely large. 1 over the infinitesimal is infinitely small. So we have to try to imagine something infinitely small. And when Isaac Newton invented calculus, he invented calculus because he needed it as a tool to solve problems, not to drive pre-med majors crazy. The integral calculus is a tremendous problem-solving tool. You have to appreciate it. You need to appreciate the differential, the infinitesimal. So when Newton came up with the idea, the bishop wrote, "Look, what are these evanescent increments? They are neither finite, nor quantities that are infinitely small, nor yet not yet nothing. Maybe we call them the ghost of the departed quantity." He's even making fun of Newton because of this idea of the infinitesimal. And of course, it makes sense. You have this idea, this thing is almost zero. You can't give it a value. You're not supposed to give it a value. And if it can't be given a value, how could it possibly be useful in an equation? So the best way to understand infinitesimals is to see where they're useful. You say, "Oh, that's pretty cool. That's neat." So here's the equations for the area of a square. This is the normal equation. The area of a square is the length of a side squared. It's exact. You should all understand that by now. The difference equation, delta A is 2s ds plus delta s squared, is 2s delta s, not d. That's exact. It works every time. The difference in the area of two squares is 2s times the side length plus the difference in side length squared. And here is the infinitesimal difference equation, dA equals 2s ds. This is also exact. We cannot plug in a number for dA. We cannot plug in a number for ds. But dA is equal to 2s ds. So I'm going to peek ahead a bit. I want to show you how this can be useful, because you're not going to believe it. So we're going to skip ahead to section 2.2, and we're going to review the calculations we performed on slope, section 3 of chapter 1. So here's what we had. This is A is s squared, and we calculated the slope at a point by drawing a tangent line, getting the slope of the tangent line. So at 2 centimeters, we did the rise over the run. At 2 centimeters, the rise is 36 centimeters, right? 36 square centimeters right here. The run goes from 10 all the way to 1. That's 9, so the slope is 4 centimeters. At 5 centimeters, it's steeper. The rise looks like 75. The run goes from 10 to 2.5. That's 7.5. So the slope is 10 centimeters. At 8 centimeters, we draw another tangent line. The rise is 96 centimeters. The run goes from 4 to 10, which is 6 centimeters. The slope is 16 centimeters. But let's look at the infinitesimal difference equation. It is dA equals 2s ds. Before we said you can't calculate the slope at a point using the rise over the run because at a point there is no rise and there is no run. But there are infinitesimal rise and an infinitesimal run. The infinitesimal rise is dA, the infinitesimal run is ds. And we can use this equation to solve for the slope. The slope is dA over ds, the rise over the run. dA over ds is 2s. So now we can use this equation instead of drawing a tangent line. So the slope at 2 centimeters we saw was 4. Instead of using the slope of the tangent line, we're going to use this equation. The slope is dA ds. That's 2s. We plug in 2 centimeters for s, and we get 4 centimeters. That's the slope. At 5 centimeters, let's use the equation. dA ds is 2s. Plug in 5 centimeters for s, we get 10 centimeters, which is the slope we got for the tangent line. If you go up to 8 centimeters, let's use the equation again. dA ds is 2s. 2 times 8 centimeters is 16 centimeters. That's the same slope we got before. So by using the infinitesimal difference equation, we get the slope at every point. Everywhere. We don't have to draw a tangent line for a different point. We don't know dA, we don't know ds, but we know that dA over ds is 2s, and that is where it's useful. So in this chapter, we're going to explore the infinitesimal difference, and we're going to start in section 2.1 with the idea of repeating decimals. So you have this decimal, 0.9999999, it goes all the way out to infinity. Is this equal to 1, or is it less than 1? Think about that before you watch 2.1.